My name is Mark Chiew from the University of Toronto, and I just want to acknowledge that some of these slides are adapted from the WIN graduate course and the FSL course physics lectures. The first part of this lecture will focus on image acquisition. And where we're going to start is the Larmor equation. I think hopefully you will have seen this in one of your previous lectures, but just to briefly summarize again, this is the equation that describes the speed of rotation or precession for the magnetization. So this omega term represents this frequency, which is the speed of rotation. This term here in purple is called the gyromagnetic ratio, and it's a physical constant. For protons, it's about 42.5 megahertz per Tesla. And what it does is it scales the strength of the magnetic field to let you know what frequency you get. And so B is the last term in green, is the strength of the total net magnetic field experienced by the spins. So the frequency is the product between these two. And this is very important because ultimately what we're going to be talking about with respect to image acquisition and image formation is how we specifically manipulate the frequency by changing the magnetic field strength using magnetic field gradients. And that is the key to spatial encoding in MRI. If we look at this breakdown of different resonant frequencies at different standard magnetic field strengths, we see that at 1.5 Tesla, we get a resonant frequency of about 64 megahertz. At 3 Tesla, that's doubled to about 128 megahertz. And at 70, that's about 300 megahertz. So we can see that the resonant frequency scales linearly with field strength here. Ultimately, though, the key takeaway here is that when the main magnetic field is weaker, we have slower frequency. And when the main magnetic field strength is stronger, we have faster frequency. And that, again, is what the gradients are going to use to manipulate the spins so that certain spins experience faster frequencies and certain spins experience slower frequencies. And we take advantage of that fact to extract spatial information from our images. Here's just a diagram of what that looks like. Again, the spins are typically always precessing around the main magnetic field, which in this diagram is up and down. And we can see in a stronger magnetic field on the right, the spins precess faster. They have a faster rate of rotation or resonant frequency. And in a weaker field, they will have slower precision, so they rotate a bit slower. If we're looking down now onto what we call the transverse plane, we can see that the stronger field precesses much faster than the weaker field does. So you may recall that there are three main sources of magnetic fields in an MRI system. The B0 main magnetic field, which is constant and always on. There are gradient magnetic fields. We call these the GX, GY, GZ gradients typically. And these are magnetic fields that vary in magnitude along a specific direction, either the X, Y, or Z direction. And these ones aren't always on, we can turn them on and off. The third way is by using F fields, but that's typically used in excitation and not typically for spatial encoding, so we're going to ignore that for now. So we're going to consider the fact that our net magnetic field is always the net sum of the B0 constant field plus whatever gradient we're adding on top of that. And I want to point out that the magnetic fields associated with the gradients are always oriented in the same direction as the B0 field. So here in this diagram, you can see that the B0 field is pointing up on the slide. And so the gradient, the direction of the magnetic field produced by the gradient always also points either up or down, but along the same axis. But the magnitude and polarity of that can change. So actually, relative to isocenter, which is the 0 point of the gradient, typically, then we have on one side we have the gradient being negative and reducing the effective field strength, and on the other side the gradient is positive, so it adds to the effective net field strength. So we'll see that the impact of that in a second, but I just want to again reiterate that when the magnetic field gradients are off, then we just have a completely uniform, ideally a completely uniform B0 field. So there's equal field strength everywhere and therefore equal magnetization precession everywhere. And we saw that here, where all the spins in this diagram were precessing with the same speed. But if we turn on a gradient, the same gradient I showed earlier, where on the left now we have this negative gradient, which reduces the effective field strength, and on the right, a positive gradient, which increases the effective field strength, then what we end up with is slower precession on the left because we have a weaker net field, and faster precession on the right because we have a stronger net field. The implications of this are actually quite profound, because what happens is that when we turn on these gradients, this generates a change in precession frequency as a function of space, or precession rate as a function of space. And what emerges are these wave-like spatial patterns of phase, or the effective orientation of the spins at any given time. And we can watch that happening here if we watch this video. And we turn on the gradient. Initially, before the gradient starts, all the spins are oriented in the same direction. So after excitation, typically the assumption is that the spins are all coherently oriented. As we turn on a gradient that is stronger on the right and weaker on the left, we'll see that the spins here on the right of this video are precessing quite fast relative to the spins on the left, which are precessing quite slow. And if we just underneath plot the phase, or the angle of the magnetization as a function of time, then we can see as time evolves and as we leave the gradient on, we start to see these sinusoidal patterns in the phase, right? Initially it starts out quite flat, then we get here about one period, and then soon 2 periods of fluctuation. And again, if we watch this animation now of turning a gradient on in the presence of spins, we see that if we turn a gradient on, initially the spins are all coherently oriented. I'll start this again here. Before the gradient turns on, the spins are all pointing to the right. And as the gradient is on for a certain amount of time, we get a certain amount of phase evolution. There's more phase evolution here on the right and less on the left, right? And so we start off with a flat sinusoid, right, which is a zero frequency component. Then after a certain amount of time, we have this half period sinusoid. If we let this continue to evolve, right, for another fixed amount of time, what we end up with is this single full period, right? And as we let it further and further evolve, what ends up emerging are higher and higher frequencies. And we call these spatial frequencies because they vary across space. But the gradient allows us to access spatial frequencies. So when we turn on a gradient, what we're doing is we're traversing this space of spatial frequencies, and the longer the gradient is on, the higher frequency we will get. Okay, so now that we know how spatial frequencies are generated from gradients, we're going to talk a little bit about the spatial frequencies themselves in a more abstract way. So we know that at any instance in time, the signal across space is defined by this specific pattern of the phase or orientation of the magnetization, right? So it's spatial frequency that depends on the applied gradients. And we call these spatial frequencies, again, because these are sinusoidal wave-like patterns that extend across space now instead of time, where we're usually thinking about frequency. And this generalizes to multiple spatial dimensions, right? So you can have spatial frequencies across 1, 2, or 3 dimensions. And in the animation in the bottom here, you can see 2 gradients along the x and y axis that forms a diagonal-looking spatial frequency pattern. And you can see on the top is just this visualization of that pattern of phase, this periodic sinusoidal manipulation of the phase across a certain direction that is, again, dictated by the gradients. So more abstractly, we can start defining characteristics of these spatial frequencies. Here I have an example where we have a spatial frequency with 2 cycles along y. We can denote this with this k variable, which is like a wave number, with ky equals 2, so that there's 2 full periods over this field of view, and no cycles along x, so it's constant along x. So the kx associated with the spatial frequency would be 0. Another example would be the opposite. So we have 2 full periods or cycles along x, so the kx variable would be 2, and 0 cycles along y, so the ky is 0, right? And so these what we're doing is we're talking through what these k variables mean and how those map onto specific spatial frequencies. And if we have kx equals 2 and ky equals 2, what we see is that we get a diagonal pattern, right? We have both 2 cycles along x and 2 cycles along y, and that leads to this diagonal pattern of phase. So each of these patterns represents one particular two-dimensional spatial frequency, and so we can fully define these spatial frequencies in terms of these k numbers, right, these k values, and we can just use those kx, ky values to label all of these spatial frequencies. So we've seen the 2, 0, 0, 2, and 2, 2 spatial frequencies. We can also look at other ones like 2, 1, 1, 2, 4, 4, 4, 0, 0, 4, and 8, 1, etc. So I think hopefully we get an idea about what these k values represent and how those translate to these two-dimensional spatial frequencies in this case. And again, if we are doing 3D imaging, right, this extends to a third dimension. It's just harder to visualize on the screen, so we're showing you 2 dimensions now just for simplicity. So these k values simply count the number of cycles of phase in each direction. And so when we talk about k-space, which you may have heard of, k-space is just the space that accounts for the contribution of each of these spatial frequencies to the
Okay.
image content or the signal content of our image. And so those k values that we were just talking about denote a particular location in k-space. So each of those locations in k-space corresponds to one of these spatial frequencies. Again, the 0, 4 component would be on the midline on the kx axis, and then up 4 points on the ky axis, right? And that corresponds to this spatial frequency. And in k-space, at that location, what our job is as imagers is to try and find the amount of energy or the amount of signal that we need to put in that spatial frequency bin in order to reconstruct our image, right? And again, in the 2, 1 k-space location, we're 2 on the kx axis and 1 on the ky axis, 2 on the kx axis and 1 on the ky axis. And, we're looking to record the value of our image corresponding to this particular spatial frequency, right? So these patterns and the k values associated with them tell us where we are in k-space, right? And the measurement process tells us how much signal we should put in each of those locations. And so the sum total signal after application of all of these patterns determines the full k-space description of our image, right? So we need to fully sample our k-space, and the extent to which you sample k-space dictates certain parameters like your image resolution and your field of view. But after you've defined a k-space that you want to map out, we basically need to put a signal value in each one of those locations in order to reconstruct our image. So really what we want to do intuitively is think of each of these patterns as like a filter on a camera. And just to provide a simple analogy, you can imagine, a camera like they had 100 years ago, before they had color cameras. The only way to reconstruct a color image was to take a photo with one color filter at a time, right? So imagine we have this scene now, and we put the blue filter on, and we acquire the blue portion of our image, and then we put the red filter on and get the red portion of our image, and the green filter on and get the green portion of our image, and then we stitch them all together, right, to get the final image. But the final image is a composite of all of these features associated with colors in this case. In the case of MRI, it's very analogous, but instead of color features, we're talking about spatial filter features, or these wave-like features, these sinusoidal patterns. So we're building up our image as a composite of these spatial patterns, and we just need to measure the weight associated with each of these patterns and then add them all up, and that turns into our image, right? So it's this process of taking sequential measurements, each one with a slightly different filter, and then adding all of those things together to get our final image. And just to bring it full circle, that the key piece of hardware that allows us to do this are the gradients, right? Because the gradients are what allow us to change our spatial frequencies, right? By turning them on or off, we're able to manipulate the spatial frequency location that we are sampling and then we measure data from those locations, right? So the gradients are this key point that help drive this whole process. And finally, once we've mapped out the entire K-space, then we use the Fourier transform to translate from our spatial frequency set of measurements to an actual image that you can look and see and interpret. And so that Fourier transform formalism is just the mathematical toolkit that we use to map from spatial frequencies to images. So one piece of intuition, I guess, with respect to how these K-space filters respond to image features is that when you're acquiring high resolution data, high resolution means finer features. And so typically what that does is it requires finer filters. So the high frequency filters, right, ones that have lots of fast wiggling, capture high frequency content in the image, right? So that's why, and those typically are located further out in K-space. So that's why we need to sample further out in K-space to get higher resolution, right? But the trade-off is that as you want to increase your spatial resolution, you need to acquire more of these filters, right? Because the periphery of K-space is larger. And therefore, the trade-off is it takes longer acquisition time, right? The more K-space you add, the more that you have to sample and the longer it takes to acquire your image. Finally, again, I think I've said this multiple times, but it bears repeating because it's so important that when we turn a gradient on, the spatial frequencies change over time. So they don't just take us to a fixed spatial frequency. You can see in the image below, as the Y gradient is turned on and we leave it on, the spatial frequency evolves over time, right? So actually when we turn a gradient on and leave it on, we don't just go to a fixed location in K-space, we move through K-space and we sample as we go, right? We call this a trajectory now. And if we turn on multiple gradients, like the X and Y gradient at the same time, we move diagonally through K-space, right? And you can see the spatial pattern here is diagonal. And again, we traverse this diagonal line and then we sample as we go, right? As we evolve, as the spatial frequencies evolve. And so when we talk about trajectories, what we're talking about really is the order or the pattern of traversal of K-space data acquisition. So again, you can imagine in the center here, we have this space where we have to fully sample all of the points in this square. But the way that and the order in which we do it is largely arbitrary, right? There are some patterns that are more efficient than others, but the specific pattern of K-space traversal is called the trajectory, right? So there's that path through K-space that is driven by the gradients. And whatever path we take, once we fully sample, then we end up with something that we can put into a Fourier transform and turn into an image. So one of the most basic and standard acquisition trajectories is sometimes called line scanning or 2D-FT or just basic Cartesian imaging. There are various names for it, but the net effect of these trajectories is just moving through K-space one line at a time where the line is perfectly horizontal or perfectly vertical, right? So we're just moving along this regular grid of K-space points. After every RF pulse, what we do is our gradients take us to the start of a different line. Right, we'll watch this happening now. And then we sample along that line, right? And if we watch it go again, after a few excitations, you can see that after the RF pulse, which starts us in the center of K-space, we go to a different line and we acquire that line. And then after every RF pulse, we go and we acquire different lines. So this is the standard in basic structural imaging, and it's basically something that is very robust and produces minimal artifacts, but is not very efficient, right? You just acquire one line at a time. It's a fairly slow process. If you're involved in functional neuroimaging at all, you would be familiar with echoplanar imaging, or EPI. It's very similar to the line scan or 2D-FT acquisition. The exception is there are two differences, or I guess several differences. So that after the RF pulse, we actually acquire all of the lines at once and not just one line at a time. So you can see actually the trajectory after the RF pulse just keeps going back and forth. So we zigzag across K-space back and forth. And so the whole readout takes quite a bit longer, right? Because we're reading out, n lines instead of one line. Another key difference is that the direction of traversal is actually reversed every other line. You can see we're going back and forth. We're not going in a consistent direction. And so sometimes, I think you may have heard in a previous lecture, that can lead to artifacts, right? Because there can be offsets between the lines. But other than that, it is still following the standard Cartesian grid and sampling the same points as you would sample in the line scanning case. It just does it in a single shot, so to speak. And it's commonly used for fMRI and diffusion imaging just because of its really high efficiency. So I mentioned that we can use gradients to create these spatial patterns and map K-space in 2 dimensions or 3 dimensions. One of the ways that we do 2-dimensional imaging is through the use of slice selective excitation. So if you want to be able to map one 2D slice at a time, you need some way to selectively excite only one slice of tissue. And so what happens is we design RF pulses in such a way so that the RF pulse used at any given time only excites a single slice. In this diagram we've shown axial slices, but obviously the slices can be oriented in any direction. And after only a single slice is excited, we do a 2D mapping of the K-space of that slice. And there are a lot of scans that are acquired this way, including, again, a lot of functional MRI and diffusion imaging. Structural imaging tends to be 3D more often than not, whereas functional imaging and diffusion imaging tends to be 2D. In the last bit of this image acquisition section, I wanted to talk a little bit about the signal-to-noise ratio. So if you're not aware, the signal-to-noise ratio is something that talks about the quality of the image, or how strong the image is relative to how much noise there is in the image. So an image with high SNR would look like this on the left with not a lot of noise, and an image with low SNR looks like the one on the right with a lot of noise corrupting the image and making the quality of it poor. And so formally we define SNR as a signal divided by the standard deviation of the noise. And so the signal-to-noise ratio essentially describes the signal robustness. How much stronger is the signal than the noise, right? And all else being equal, we typically want the SNR to be maximized. Here's just an example of what some SNR values look like. If SNR equals 1, that means the signal is about the same order of magnitude as the noise, and that ends up in an image like you see on the top left, which you basically cannot see the brain at all. As we increase the SNR, you can see the brain emerging from the noise, and once you get to an SNR about 20 and above, you start to get what looks like clean brain images, right? But there are definitely scenarios in which we are acquiring data in poor SNR regimes, and if you are doing so, you need to be aware of the impact of that on the quality of your data, whether you're using it for research or clinical diagnostics or what have you. In terms of the protocol choices that you can make during image acquisition that affect SNR, there are many factors. The types of RF receive coils that you choose, the field strength of your magnet, the timing of the sequence in terms of the readout bandwidth, the TE and the TR, the voxel volume or the image resolution, the total scan duration or the amount of time that you spend imaging, and really anything else that affects the signal, so to speak. Most commonly when you're at the scanner console, the easiest choices you have to make are about what resolution you want, the voxel volume, and how long you're willing to scan for. One of the easiest ways to increase SNR is by averaging, and so you can scan for longer, get multiple averages, and increase your SNR, but that incurs a penalty to time and the amount of time that you spend acquiring data. So again, it's a choice that you have to make with respect to your protocol. So here's how SNR relates to acquisition time. We know that I've just said that longer acquisitions produce less noise and higher SNR, but actually that improvement is not linear. So scanning for double the amount of time doesn't double the SNR. Unfortunately, it actually only improves with the square root factor of scan time. So if you want to double your SNR, you need to scan for 4 times longer. So we can see just an illustration of that process here. So actually to get from a really noisy image to a really clean image, you have to take an actually really high number of samples because of the square root impact of the number of averages. So there's diminishing returns. In terms of voxel volume or image resolution, it's more simple to understand. Larger voxels have more signal in them, right? And so that does scale linearly. So SNR scales linearly with voxel size. And again, if the bins get larger, there's just more signal added together, and therefore you get higher SNR. So it's proportional to voxel volume. So if you double the dimensions of a voxel on each side of this cube, you go from a 1 by 1 by 1 voxel to a 2 by 2 by 2. That has an 8 times volume increase, and therefore an 8 times higher SNR, right? So the trade-off, obviously, is that you have one giant voxel instead of 8 voxels. But the trade-off is fairly straightforward to understand with respect to SNR and resolution. So you can also average data to achieve high resolution if you want. But unfortunately, averaging only has a square root improvement. So you can average data, but in order to get an 8 times SNR back from this averaging process, you need 64 averages to recover that factor of 8 SNR. Okay, so in this last part of the lecture, I'm going to talk a little bit about image interpretation and analysis. The first thing I want to do is just orient you with respect to images, brain images in particular, because that's what I work with. But if you are like me and you come from an engineering or physics background, you may not be used to thinking about images using these types of labels. So the first one I want to define for you is the transverse or axial plane. This is usually cutting through the brain where the plane is perpendicular to the axis of your spine. Typically results in images like you see here on the right. Some other labels that we use that are relevant clinically in describing and orienting yourself within this image is that the anterior portion of the brain is the forward-looking one, where your eyes are, and the posterior region is towards the back of your head. If we're talking about the coronal plane, then we're talking about slicing through your head from top to bottom, right? And when we're in the coronal plane, like we are here, we use the term superior to refer to the top of your head and inferior to meaning towards your neck and down towards your body. And here, I've not labeled left and right, but we'll talk about that in a second. And finally, the sagittal plane is slicing. Imagine a slice now placed between your eyes, down, cutting across your head. And in this sagittal image, we can see the superior and inferior regions again, top and bottom, and then the anterior and posterior, so the front and back regions. We can also have oblique slices, so depending on how your acquisition is oriented, you may have oblique slices that cut at an angle. Or typically, if you have 3D acquisitions that have sufficient resolution, you can actually reorient in post-processing and re-slice your data in any orientation you would like, and sometimes that helps, particularly with a visualization of certain features. So oblique slices don't have names, so to speak, but any slice that is not either purely transverse, coronal, or sagittal is an oblique slice. So I mentioned left and right. I just want to touch on this concept of display conventions for brain images in particular, which is left and which is right, because there are actually, confusingly, 2 different conventions for displaying brain images. So radiological convention is actually where right and left are reversed on the image. So like in the image you see here, the right-hand side of this person's body would be on the left-hand side of this image, and the left-hand side of the person's body would be on the right-hand side of this image. And that's because, actually, the perspective is that we're viewing this brain standing from the feet, right? So we're looking from the bottom, and that's why left and right are reversed. There's another convention, which is called neurological convention, and that's where the right-hand side is on the right, and the left-hand side is on the left. And that's because now we're viewing the brain from the perspective of looking from the top. So looking top down, and so right is right and left is left. But if you're looking from the feet, everything is reversed. And so the convention that you use depends on context and depends on the person. But these two different conventions exist, and unfortunately, because the brain in particular is symmetric around the left-right axis, then it is important to label your images very carefully and keep track of which is left and which is right, particularly if you're doing things like functional imaging or analysis, where it can be important to know whether you're talking about the left or the right, but it's not obvious from looking at the image because it's symmetric, and so either way would look fine. One of the things I want to talk about now are image contrast and the concept of weighted images. So most of the images that you acquire, if we're talking about structural imaging or functional imaging or diffusion imaging, they're diffusion, or sorry, they're contrast weighted. So that means that typically one parameter is more heavily weighted or more heavily influences the image contrast. But the contrast is not quantitative, and it contains contributions from other parameters. So for example, a T1 weighted image is one in which the contrast is driven by the T1 longitudinal relaxation parameter. And again, in the brain, all my examples are in the brain because I work with neuroimaging. In the brain, a T1 weighted image typically has gray matter that is gray, and white matter that is white, and fluid or CSF that is dark, right? And the way that you generate a T1 weighted image is typically with a short TR, because you want to be sensitized to the T1 relaxation, and a short TE, because you don't want to be sensitive to T2. A T2 weighted image is one that's driven by weighting by the T2 transverse relaxation parameter. And again, in the brain, a T2 weighted image has gray matter that is actually light and white matter that is dark. So the contrast is inverted from the T1 weighted image. But also the fluid or CSF, as you can see here in the ventricle, is very bright. Right? So that's one characteristic feature of T2 weighted images. The way that you generate a T2 weighted image is with a long TR, because you want to be insensitive to T1, and a long TE, because you want to be more sensitive to T2. A proton density image is where the contrast is driven basically just by the spin density or proton density of the tissue, so how many spins there are in any given compartment. In the brain, a proton density image typically has gray matter that is light and white matter that is a little bit darker, but there's actually very little contrast between the brain tissue and the fluid because they have roughly equal proton or spin density. The way that we generate a proton density weighted image is by choosing parameters so that we're insensitive to both T1 and T2. So we use a long TR so that we have full T1 recovery, and a very short TE so we don't have much T2 decay. Finally, the last one I wanted to talk about was a bit of a special case, but you see it very often, especially in neuroimaging, is a FLAIR image. FLAIR stands for Fluid Attenuated Inversion Recovery, and typically it's T2 weighted. But the difference between a FLAIR image and a T2 weighted image is that the CSF signal, the fluid signal, is actually null, right? Or attenuated in this case, as you can tell in the name. And so the advantage of this, though, is that the tissues with high bound water content are still bright, but now you don't have confounding signal from free fluid like CSF near ventricles and near brain boundaries. So you can more easily visualize, as you can see here, areas of edema or other kinds of pathologies that involve water infiltration. And this is generated with an inversion recovery sequence, so that inversion recovery is what's needed in order for us to null or attenuate this free fluid signal. So in contrast to weighted images, there are ways to acquire quantitative MR images. And when we say quantitative, that what we're actually referring to are the fact that we are mapping not just voxel signals that are contrast weighted with some parameter, but actually we are recovering the T1 or T2 parameters themselves. So we're performing a mapping experiment where we actually try and infer what is the T1 value or the T2 value in this voxel. And so instead of a unitless complex signal amplitude that is a mix of multiple factors, the signal that we place in any given voxel actually refers to this specific biophysical parameter, and it has real units, like milliseconds, right, in terms of these relaxation time constants. So on the right here, you see a T1 map, right, an example T1 map, and you see a scale here, and these numbers actually correspond to the T1s in milliseconds, right? And again, you can see the CSF has a really high T1 because fluid has a high T1. The gray matter has an intermediate T1. Typically at 3T and 7T is 1500 to 1600 milliseconds, which you see here. And then white matter has a slightly lower T1, which is why it's a bit darker, right? Closer to 1000 or somewhere in that range. Quantitative imaging allows for our measurements to be more easily compared across scanners and sites, because now we don't have all of these extra factors like coil sensitivities and other scanner related gains and things like that confound the level of signal that we measure in our images. If we have quantitative units attached to the parameters that we measure, then these are more easily translatable in terms of cross-scanner and cross-site comparisons. It also allows us to quantify changes due to pathology or interventions in terms of physical units, again, because signal changes, you can always represent things as percent signal changes, which we often do. But it's not, in some cases, it is beneficial to understand quantitatively what exactly has changed in a specific physical unit. So the caveat really is that acquisition of quantitative images is more involved than standard weighted images. Typically, the experiments are a bit longer. You need to do more. You need to take more measurements in order to tease out the quantitative T1 or T2 parameter. Here, you just see a T2 map, which is analogous to the T1 map, but with the shorter T2 values. But instead of just measuring a single weighted contrast, you typically have to make multiple measurements to be able to extract what the underlying relaxation parameters are, so that they can be more complex to acquire and interpret. So one of the things I mentioned in terms of cross-site comparisons is that signal can have arbitrarily weighting or gain associated with the scanner and the coil you choose. One of the factors that plays into this is something we call the bias field. And the bias field reflects the fact that when we generate images naively from the scanner, they can have a non-uniform intensity, right? So like the signal here, for example, in this sagittal image of the brain, is bright towards the top right, and the surface of the brain, but it gets darker as you go down. And that darkening of the signal doesn't reflect anything about the real signal content of the magnetization that is in this person's brain. Right, the gray matter isn't actually darker down here than it is up there. It's mostly actually due to the weightings associated with things like coil sensitivities and, to a lesser extent, transmit field inhomogeneity, right, depending on which field strength you're operating at. So the fact that the image is dark down here it's not reflecting less signal from the person. It's reflecting less signal received from the measurement process. So we typically want to remove that factor so that we can interpret the signal across the brain in a more uniform and comparable way. And so we typically do this by bias field correction. And you often want to do this before you do any quantitative analysis on the pixel values, because again, signal values would be darker or lower down in one part of the brain than they are in another, and you might erroneously attribute that to some biophysical change where actually it's just an artifact of the measurement process. So I'm not going to go into too much detail about these bias field correction algorithms, just to say that they exist and they are a common part of post-processing in neuroimaging in particular. And when you apply these algorithms on an image that looks like the top, then you get something that looks like the result in the bottom, which is it's the same brain, but now the intensity of the image has been normalized so that the dark regions are no longer artificially dark, but this reflects what the true magnetization was across the brain. It makes it easier for us to now compare the signal values from one part of the brain to another, or across scanners or across individuals, because this effect of this non-uniform shading or weighting has been removed. One of the things I mentioned before when we were talking about SNR is the fact that you can recover SNR by reducing your voxel size, right? Because larger voxels mean higher SNR. But one of the downsides of that is that you get what we call partial volume effects. And partial volume effects arise because we have typically in MRI voxels that range from 0.5 millimeters to about 3 millimeters on any given axis, depending on the type of sequence you're working with and the type of data you're collecting. But partial voluming at these scales means that in a 3 millimeter voxel, your voxel is not going to be homogeneously filled with exactly one type of tissue, right? You imagine a voxel that is on the boundary of gray and white matter. It could have 50% gray matter, 50% white matter, or at any other type of tissue boundary. These effects mean that you have contributions from multiple signal compartments in a given voxel, and that can also lead to confounding interpretation, right? Because you want to typically associate a voxel with a signal level and try and interpret that in terms of whatever analysis you're doing, but you depending on your resolution, you may need to be mindful that signal is actually the sum of multiple components. So the way, obviously, to address that is typically by just acquiring higher resolution, right, or smaller voxels, because you have a reduced partial volume effect if you reduce the volume of the voxels, which makes sense. But the cost of that is increased acquisition time, right? And just on the right here, you see a diagram. Right? It's the same image, but it's been downsampled multiple times. So you can see in the high resolution image, right, on the right, you can see regions of the brain where you can see really bright vessels, right? And in the intermediate image, you see vessels that are less well defined. And actually in the low resolution image on the left, you can see some of those voxels, the presence of that vessel has disappeared or has been absorbed through partial volume effect into the other voxels. So even though the signal is still there and it still contributes, it may not be obvious because it's now hidden within these partial volume effects. So you have to be careful when you're interpreting your data. I'd like to thank you for your attention. Please feel free to contact me at mark.chiew@utoronto.ca if you have any questions.